Hey everyone, and welcome to today's Explainer. We are jumping right into something completely fascinating today, the foundational laws of chemistry. We're going to visually unpack the hidden rules that govern, well, literally everything around us. So let's get right into it.
Now, picture this. You burn a log of wood or you mix two totally different substances together. What happens to all that stuff? Does the mass just vanish into thin air? It's a classic question we've all probably wondered about at some point. When things transform, where exactly does the mass go?
So, here is our big question for today. Does mass actually change during a chemical reaction? Take a second and make a quick guess in your head. Do you think the overall weight goes up, goes down, or stays exactly the same? Let's find out.
Section 1. The balloon experiment. We are going to figure this out with some solid visual evidence right here in our virtual lab. Take a look at this setup. We've got a digital weighing balance, and sitting on it is a flask with about 20 milliliters of vinegar. Right next to it is a green balloon holding around 2 grams of baking soda. Keep a close eye on that exact total mass displayed on the scale right now before anything happens.
Okay, here comes the fun part. We attach the balloon to the flask and dump that baking soda straight into the vinegar. Boom! Instant reaction. You can actually see the rapid bubbling and fizzing inside the flask. This is clear visual proof of a highly active chemical reaction taking place right before our eyes.
As you can see, the gas released from that reaction completely inflates our green balloon. But check out the reading on the balance. Even after all that chaotic bubbling and the balloon expanding, the total mass is absolutely identical to our starting number. Mystery solved. No mass was lost and no mass was gained.
Section 2. Mass conservation kinetics, or the rule of mass conservation.
That little balloon experiment actually proves something profound. Matter doesn't just disappear, it simply changes form. The brilliant guy who formalized this rule is Antoine Lavoisier, widely known as the father of modern chemistry. Way back in 1789, after running tons of super strict, highly controlled experiments, he introduced this universal rule to the world. Reading his original words is incredibly powerful. He proposed that in every operation, an equal quantity of matter exists both before and after the operation. Today, we officially call this the law of conservation of mass. Basically, you literally cannot create or destroy matter in nature.
Let's actually look at the math backing this up. Say we mix 4 grams of calcium carbonate and 2.92 grams of hydrochloric acid. The total mass of our starting materials, the reactants, is exactly 6.92 grams. Now, after they react, they turn into carbon dioxide, water, and calcium chloride. If you add up the weights of those 3 new products, guess what? It's exactly 6.92 grams. It is a perfect mathematical proof.
So the huge takeaway here boils down to this one simple formula. The mass of your reactants is strictly equal to the mass of your products. The exact mass you start with is the exact mass you end with. The atoms didn't pack up and leave. They just rearranged themselves into completely new combinations. Section 3. Law of definite proportions. Okay, so if mass is perfectly conserved, how do elements know exactly how much of each other to combine with to form a specific compound? History gives us a really colorful answer. Look at this red pigment used in ancient painting. It was known as cinnabar in Rome and hingula in India. Ancient scientists noticed something wild. No matter where on Earth you mined this rock, it always contained exactly 86.22% mercury and 13.78% sulfur. This fixed, unwavering ratio totally baffled the ancient world.
And that exact same mathematical rule applies right in your own kitchen. Take everyday table salt, or sodium chloride. The strict mass ratio is 23 to 35.5. Grab a grain of salt from literally anywhere in the world, and 23 mass units of sodium will always combine with exactly 35.5 mass units of chlorine. This unbreakable mathematical rule of nature is called Proust's law, or the law of definite proportions.
Section 4. Crystal K and R, or inside the crystal. But why are these elements so strictly obedient to these proportions? Well, let's zoom way in, past our normal vision and look at the microscopic structure of a crystal. This 3D structure isn't just a random pile of elements. It is a perfectly ordered, repeating crystal lattice. Every single positively charged sodium ion is locked securely in place, surrounded by exactly 6 negatively charged chloride ions, and vice versa.
Because atoms have to lock into these precise spatial patterns to chemically bond, they simply cannot randomly alter their proportions.
Now, when atoms combine while strictly obeying these two fundamental laws we just covered, the final stable structure they form is called a molecule. A molecule is essentially an electrically neutral entity made of multiple atoms that can exist all by itself, while still displaying all the unique chemical properties of that compound. The very fact that molecules exist at all is rock-solid proof that both the law of conservation of mass and the law of definite proportions are working flawlessly around us every single day.
And that brings us to the end of today's explainer. But a curious mind never really stops learning. So I want to leave you with one deep, provocative thought to chew on. Are there any chemical changes out there that actually do not obey the law of conservation of mass? Could there be extreme conditions in science that manage to break this universally accepted rule? Keep thinking about it, keep exploring these incredible mysteries, and I'll catch you in the next explainer.